So looking at IPsec in a little bit more detail, we see some of the underlying components that make it function. Let's start at the top with IKE. IKE is Internet Key Exchange, and this is responsible for policy negotiation. That is, when traffic comes into a router and that traffic needs to be protected, we look and say, is there an existing tunnel? If there's not, we need to establish one. This happens by creating a connection to the other side using UDP 500. And this is where our negotiations are going to take place. Whether you're using IKE v1 or IKE v2, both use UDP 500, and they discuss how are we going to encrypt this traffic for the end users. This is really a management session. Once this is established, it's called an ISACAMP security association. We go on to create an IPsec security association. And that's where ESP will be applied to end user data. So here we have a user, A, they send traffic to the router. The router determines that this is traffic that needs to be protected and encapsulates that traffic in ESP. That's what's used from router to router. Now, when this ESP segment comes into this router, we look at it, we identify something called the security parameter index. We associate it with the security association that says this is how you'll decrypt that packet. We decrypt the packet, and now clear text traffic comes out. So again, IKE is for the policy negotiation. Once our ISACAMP essay is established, we build an IPsec essay. And the IPsec essays, inbound and outbound, are for passing the end user data. So our data is handled here, and management, keying material, are handled here on that ISACAMP essay. So IKE is a standard. It's documented in RFC 2408. It uses a phase-based approach to establish security associations. That just means you've got phase 1, which defines your management session, and you've got phase 2, which creates your data session. That management channel is called an IKE security association, and the data essay is referred to as IPsec security associations. If you were to do a debug, if you were to look under the hood and see what's happening with this connection, you'll see that during phase 1, we're either operating in what's called main mode or aggressive mode, depending on how we're handling authentication. Once this negotiation completes successfully, we move into IKE phase 2. And at this point, we're inside of something called quick mode. This is useful to know if you're troubleshooting, but for the most part, if we have all of our parameters set up appropriately the first time, it's just going to kick off and work. It'll complete our aggressive mode, jump over to quick mode, and our tunnel should be up. Additionally, there's a capability called PFS, or perfect forward secrecy. It says once our tunnel's up, once everything's been established, we want to use this secure protocol called Diffie-Hellman to negotiate our new keying material. It says even though we've got a VPN tunnel, when it's time to negotiate new keys through that tunnel, we want to do it in an encrypted method. And this is just more secure. It's called perfect forward secrecy. IKE version 2 came out several years later, and it gave us quite a few features. It gave us some improvements, and it was really a protocol update. It took everything that had kind of been missing from IKE version 1, all the things that we said, why didn't they do that right the first time? And they basically baked it in the second time. Gives us stronger security, gives us some DDoS prevention. One of the real neat things is that it gives us a standard mechanism for establishing remote access VPNs. In other words, we're saying that with IKE version 2, you could use just IPsec as a standard built into your operating system, Windows, Linux, or OS X, and establish remote access VPN connection. You don't have to have a Cisco VPN client in order to do it. Now, it's nice to have the Cisco VPN client because it does a whole lot more, but the fact that remote access capabilities have been standardized is a really big step forward. So taking a little bit of a closer look at what happens with ESP, you've got a user, and let's say that user is doing a remote desktop session into a remote computer at another office. So our data here is going to be TCP because that's what remote desktop uses, and carrying some RDP payload. Now, the original IP header, this is RFC 1918. This is private addressing. It doesn't have to be, but it typically is. And that's because we've got private addresses at each of our office. I've got computer A trying to RDP into computer B. Now, all this traffic is going to be protected. And then what goes on the outside of it is the ESP header. Remember, this is a layer 4 header, no port numbers, but it does have something called an SPI. That SPI is used to link this encrypted packet to a security association so we know how to decrypt it. Next, we've got a new IP header. So it's like, what? I've got 2 headers? These are the parties that are communicating in the original IP header. This new outer IP header is going to have the public addresses that were used to communicate across the internet. Now, when I say it's private and public addresses, I'm just talking about a typical implementation. You could use this inside of an organization, and it could all be private addresses, or you could use it with all public addresses. Just talking about typical deployments. Now, what we see here is something I mentioned earlier. I said, if I try to send an ESP segment through a PAT device, here's my router, it's doing port address translation. Packet comes in, we go in here to grab a port number, and we go, what the heck? There's no port number. Well, the ASA can actually do port address translation by paying attention to the security parameter index. It's pretty fancy. Most devices don't do things like this. That is to say, if you've got a user, they're out in the field, maybe they're at a Starbucks, they bring up a VPN, who's to say that the Starbucks VPN is going to support NAT-Traversal? You see, NAT-Traversal takes what we were just looking at in the last slide, in this ESP header, which has no port number, so it could fail in PAT, we go, oh, we can fix that. How would you fix it? We go, well, we'll just take ESP and we'll encapsulate that inside a UDP. And you go, holy headers, Batman. We've got IP header here, we've got a TCP or UDP header here, we've got another UDP header over here. You know, what's going on with our MTU is we add all this additional overhead. And a lot of times, it's going to go down. A lot of people will say, automatically slide that MTU down so that you don't get fragmentation with all these additional headers. Well, the reason we had to add this UDP header, and this is going to be on UDP 4500, is so that we can go across a PAT device. Now, with SSL VPN, we don't have to worry about all this. Another piece that could screw us up is what happens if they're not allowing UDP 4500 out through their firewall. Maybe the administrator doesn't know how NAT-Traversal works. If they're only allowing certain ports and they forget this one, our users are not going to be able to authenticate.